Welcome to our 2020 Power Electronics webinar series. Thank you for joining us today. Today we bring to you design consideration for transformers in full bridge phase shift converters, presented by Jose Molina and Lucas Niasefta. Today's webinar will be live and is being recorded and will be placed on the PELS Resource Center. We invite you to use the questions function on your panel to ask any questions you may have regarding the content or any broadcast-related issues. Questions regarding content will be answered verbally at the end of the webinar. I will now welcome Jose and Lucas to give some welcoming remarks and begin their presentation. We hope you enjoy the webinar.
Hello to everyone. Thank you very much for the introduction. I'm Jose Molina from Frenetic. Here with me also is Lucas Niasefta. I'm happy to see a lot of people connected today for this webinar about the full bridge phase shift transformer. Well, first of all, I'm going to make a brief introduction of who we are, who is Frenetic. Well, we are a group of 25 mathematicians, power electronic engineers, mechanical engineers, physics that are building great magnetics using artificial intelligence and helping companies to manufacture them in the best possible terms. We work in more than 15 countries around the world, especially in automotive, space, industrial application, and aircraft applications. Well, during this technical presentation, we are going to review the full bridge converter behavior and some key parameters that we have identified, like key parameters for designing a full bridge converter, let's say. Then after that, my colleague Lucas will talk of a specific design case of a transformer for a full bridge phase shift, where he will present one of our latest secrets, let's say, because we have made a patent of one structure of a magnetic, and we will show this at the end of the presentation. Then please be connected until the end. That is going to be the best. Now I'm going to start with the most basic part, let's say the boring part. The full bridge phase shift, as all of you know, is based on 4 switching primary. Then we have this bridge connected to a transformer. And in the case of the unidirectional full bridge phase shift, we have in the secondary 4 diodes in a with a synchronization, or we have 2 diodes when we have the secondary with center tap. Now we are going to talk only about this classic case of the secondary with center tap, where we have also in the output the inductance. Let me see if I can use the pointer here. Okay. Then this converter can behave as a voltage source when we have the output inductance here in the secondary side, but also we can have this inductance in the input, and it could be like a current source. It's very common to use this topology in industrial or telecommunication application for higher power levels above 300 watts, and allows us to include galvanic isolation, of course, because of the transformer, and high efficiency. Reviewing how this topology works, just reviewing the main intervals, main states, we can see that if we treat, when we have on the switch of the diagonal M1, switch 1 and switch 4, we are applying the input voltage source directly to the transformer. And then in the secondary side, the diode D1 is conducting, and then we are charging the inductor here during this interval. Then, if we go directly to the interval where we switch on M3, neglecting the intermediate dead time where we have zero voltage switching that we will talk later, Now we apply 0 voltage to the transformer, and in this case, then in the secondary, we have conducting both diodes, and we are discharging the inductance. The last basic stage is when we switch on the other diagonal. Then we have M2 and M3, and we are applying the negative voltage to the transformer of the input voltage. And in this case, we are again charging increasing the current in the inductance, because in the inductance here in the output of the rectification diodes, we will have the voltage in the transformer, but in the rectified way, then it's going to be applied directly to the inductance and to the LC filter in the output. Well, now we are going to review which are the key parameters that we consider really important for designing a full bridge phase shift converter. We are going to talk about soft switching for the full bridge, layout considerations, the number of magnetics that can be used. That is one of the main parts of this presentation. Some of the oscillations between the inductance and the output parasitic capacitance of the diode, and the effective duty cycle. Then, starting with the effective duty cycle, this is a very key aspect, because sometimes we have to calculate the turn ratio for Y input voltage range, and we have to consider this effect. This effect occurs because when we apply a voltage in the transformer, like we can see in the picture. Here we can see in the picture. Here we apply this voltage to the transformer. Due to the leakage inductance here, we have this slope applying in the current, and the real voltage that at the end we are able to use in the transformer is the one that we see here. Then the effective duty cycle is not the original one, is this one that we can see below. This, when we review the equations, we realize that there are two main elements that have influence. First is the leakage inductance and the load state. That means when we review the equations that this is affecting directly to the calculation of the turn ratio. And this is the main reason why we have to take care with this, especially for Y input voltage range. The next topic to talk is the oscillation that we can find between the leakage inductance and the output capacitance of the parasitic capacitance of the diodes in the secondary side. Let me delete all the delete these. Well, the oscillations that we are talking about here are due to the resonance between the leakage inductance and the parasitic capacitance of the diode. In this case, it's something that can be solved with different techniques, especially we have to take care with the layout. But here I would like to highlight that the effect is also can be controlled with the values of both elements. In this case, this effect can be seen that when we have 3 microhenries in the transformer, the peak value of this oscillation is around 120 volts. While when we just with exactly the same circuit and we put 6.5 microhenries in the transformer, the peak is more than double. And the problem here is not only the peak, is the derivative, the DVT applied to the semiconductors that can include, can make appear some failures in the system. The next topic is that the layout considerations is very important to highlight that there is 2 main phenomena here to discuss. One is the changes in the voltage in specific nodes. For example, here in this in this node here, what we have is that the voltage is changing from the input voltage to zero really fast, and I'm sorry, and then what we see is that we have a lot of problems here related with the MI emissions. Also, in the first loop, if we consider that this is not a voltage source, is the capacitor, and we are measuring the input current to the bridge to make a peak current mode control, for example, we have to take care of this loop and made as minimum as possible, because the liquid parasitics, I mean the inductance parasitics that we will put in the loop will create some spikes in the voltage in the transitions, because of the derivative voltage applied when there are changes. And one of the most important topics that we will see that are really relevant related with the transformer is the achieving zero voltage switching, soft switching techniques in this converter. And this is almost mandatory, because we have to prevent reduce the MI noise. We have to increase the efficiency with the losses, and also increase the reliability of the semiconductors. And if we take which are the main three parameters that are important for achieving zero voltage switching, we have selected these three ones: the parasitic capacitance of the semiconductor. Actually, I will not call C in. I would say, well, is C os. The magnetizing inductance of the transformer, and the liquid inductance. If we take the papers of the literature, 30 years ago, Sabater was explaining very good in a paper how to make the calculations for this phenomenon, and also some papers of Ridley. The idea is that we have some energy stored in the capacitor of one semiconductor, and during the dead time, we have to discharge this capacitance and move this energy to the complementary, to the downside semiconductor. Let's say if you have all the energy stored in M1 because is off, and M2 is conducting, and we are going to switch off one of them, we have to move the energy from M1 to M2 or reverse. And for that, what we are going to use is the energy stored in the liquid inductance. Then the energy stored in the liquid inductance, we have to comply with this equation that we can see here in the left part of the slide, where we say, well, we need to have more energy stored in the liquid inductance than in the capacitance in order to discharge. I'm not considering the energy stored in the parasitic capacitance of the transformer, because I'm assuming that we have made a design with low value of parasitic capacitance of the transformer. But in the case of the planar designs, we have to include this capacitance in the equation. And as you can see, the energy stored in the capacitor depend on the value of the capacitor, that will depend also of the voltage, but it would be constant independently of the power level of the load, while the energy stored in the inductance is totally dependent of the current. Actually, when you are working at almost zero power level, you have zero energy stored in this liquid inductance. Then one of the solutions that have made in the literature, well, you can be working with zero voltage switching at low power levels, but also you can work at adding an additional inductance. In this publication with Richard Redl in the 90s, he introduced this additional, he explained this additional resonant inductance that allows you to increase the number, the energy stored there for achieving zero voltage switching. The only problem is that we are increasing the number of magnetics in the system. At the end, we will need 3 magnetics for this full bridge phase shift instead of 2. Last point to comment for the soft switching techniques is that at very low levels, it is also common sometimes to use the magnetizing current to achieve zero voltage switching. It is important to highlight that the energy stored in the different inductance is used instantaneously. Then you need to have the energy when the commutation occurs. Then here, when the commutation of that we see in the picture occurs, we have maximum energy stored in the magnetizing inductance. Then sometimes for a specific case of low power levels, we can use it. The only problem that we will comment later is that with this current provoke losses, because at the end it's circulating current that is around the circuit. But depends of the impact that you can make a trade-off to choose to use this energy or to have a very high value of magnetizing inductance and reduce the value of this energy, because this current is independently of the power state. Of the power level. This is dependent of the input voltage, like the energy stored in the parasitic capacitance of the semiconductors. And now my colleague Lucas is going to explain a specific design of magnetics for the full bridge phase shift. And well, this is the interesting part of the presentation.
Okay, Jose, thank you. So hello to everyone. I'm going to show you a step-by-step procedure for designing the magnetics of the phase shift full bridge. So for this particular case, we have selected our 400 to 48 volt DC-DC converter, typical in telecom applications, with 500 watts power in the output, 20% current ripple, and a switching frequency of 180 kilohertz. The full load efficiency target is 95.5%, and there is no cooling. So let's start. The first thing, the first thing to look at is the turns ratio of the transformer. We have 3 things to consider. The first one is we need to ensure enough current for zero voltage switching. So the lower the turns ratio, the higher the current circulating in the circuit. As you can see here in the 2 pictures, the one in the left, we have 500 watts output with 4:1 turns ratio, and we have a current of 2.6 RMS, while in the one in the right, we have 5:1 turns ratio, and we have a current of 2 amps. So at the end, it depends on which current level do you need. If you need the lower the turns ratio, you could extend also the zero voltage switching for light load. Then the second thing to look at is that you have to be able to deliver full power at minimum input voltage, taking into account the duty cycle loss given by the leakage inductance. And the last thing is that the voltage spike that is shown in the synchronous rectifier MOSFET and in the diodes is inversely proportional to the turns ratio. So the larger the turns ratio, the lower the voltage spike that you are going to see. So with all of this in mind, with this particular case, we have selected a 5:1 turns ratio. Then the second thing to look at is the magnetizing inductance. That here there are 2 things to consider. First is which is the target, if it's a low inductance value or a high inductance value. So what I mean by low, high, normally low value is in the range of 100 micro to 300 microhenries, and high inductance value normally is above 1 millihenry. So if we need a low value, then we will need to add some gap in the ferrite core. This will give us a good tolerance on the inductance, which means that we will have the inductance value with a tolerance around +5, +8%. While if we have a very high magnetizing requirement, this means we need to have a lot of number of turns in the primary side. In order to have, and then we will have to rely on the tolerance of the core, which is plus minus 25%. Otherwise, adding the minimum gap will involve too many turns, which will imply very poor performance. And then the last thing to look at is how is the converter control. If we have a peak current remote control, we need to ensure a low magnetizing current. So we need to ensure a high magnetizing inductance, which is the case of our current design. So we select a magnetizing inductance of 3.6 millihenries. Then the third thing to look at is the resonant inductance that we need for the zero voltage switching. So here we have to define which is the power range in which we want to have the zero voltage switching. For this particular case, we have selected from 50% load to full load. And this equation is given by a reference design guide from Texas Instruments. You can find the reference at the end of the presentation. We have used MOSFETs with relatively low output capacitance, which give us 56 picofarads. So this means we need a total resonant inductance of 14.5 microhenries. So here, many times we find now a key question, which is, shall we have this inductance as the leakage inductance of the transformer? Shall we have minimized leakage inductance? So this means very good efficiency in the transformer and then place an external value. What is better? The answer is not straightforward at all, because we have to consider many facts. First thing is that the leakage inductance is difficult to predict and it's limited. When I mean limited, I mean that each shape will have a certain geometry where you can locate the wires in a certain way. So you will have 2-3 different possibilities to locate the wires. So then you will have 2-3 different leakage inductance. And if those values are not within your range, then you will need to add an external inductor or you will need to go to a customized shape. Then the second thing is that high leakage inductance means poor coupling in the transformer. So this means poor efficiency, and we don't want this. So many times it makes no sense to reduce the volume by making the performance poor, because high leakage inductance usually means high proximity losses. And then the last thing, as we saw before, is that at the end, the higher the leakage inductance, the higher the voltage spike in the secondary side. So we might need to add an active clamp or an RCD snubber that at the end is more components and losses. With all of this in mind, we have done a design with 3 different configurations, same wires for the primary and the secondary side, but 3 different configurations. The one in the left is with interleaving arrangement, which means that we have half of the primary turns in the first layer, then the full secondary winding, and then the other half of the primary turns. So this is a relatively good coupling, and this gave us 3 microhenries of leakage inductance, which is already a considerable size. Then we decide, okay, let's see what happens if we don't interleave the windings, which value would we get? So we did all primary winding, then all secondary winding, and we got 6.5 microhenries. We need 14 microhenries, but still very far from our target. So, okay, let's see what else can we do. So we decided to do a 2-chamber winding, which is typical, for instance, in LLC applications. And this winding arrangement allows to have very high leakage inductance. As you can see here, we multiply almost by 10 times. But looking at this, you also have to think in the proximity losses, because in this case are going to be very high. So the second thing is that we need 40 microhenries. We have 32. This is too much energy storage. This is not good for the circuit at all. So with all of this in mind, we believe that the best procedure in this particular case is to have the transformer optimized and then add an external inductor for having a total resonant inductance of 14.5 microhenries. Then the last magnetic, which is the output inductance, is kind of straightforward. It's given by the it's by the frequency, which is double the frequency of the full bridge, by the output ripple that you want, which normally is 20% of the output current. In this case, 2 amps, we need 21.8 microhenries. So we have this this picture here that is 11.5 microhenries, 5:1 turns ratio, and 21.8 microhenries in the output as the target. Then the series inductance is an inductor where we have energy storage. We need to have some gap to store the energy, and we want to design the inductor to be quite far from saturation and to distribute the power losses between the core and the windings. And in the case, well, the target loss is 0.6 watts for this case. In the case of the transformer, we want to have a very good balance between the core and the windings to maximize the efficiency of the system. We need to ensure for sure creepage and clearance distance, so we're meeting the isolation standards. And there is one thing very important, which is we need to think how we place the wires, because the secondary winding has to be placed in such a way that both of the windings have the same DC resistance and have the same or similar leakage inductance. Otherwise, one winding will carry more current than the other, and this is not interesting at all. Well, the target loss for this current design is 4 watts in the transformer. And then we have the output inductor, which characteristic is that it has a high DC bias with a low AC ripple, which means that the core losses is not negligible, but they will be very low. What we want to have is an inductor that will be not in saturation, of course, but near the saturation of the material with some enough margin, so we could reduce the number of turns and reduce the cap of losses. So with all this picture in mind, we have done a design for each of them, which is we have a PQ3215 for the inductor, which gives us 0.42 watts and a temperature of 62 degrees at full power. As you can see here, the winding losses are mainly in the windings. This is not, I mean, this is, we want it to be like this. You will see why in future slides. Then we have the transformer, which gave us a good performance, 3.77 watts with maximum temperature of 83 degrees, and the output inductor with a PQ3220i with 1.5 watt. As you can see, it is not casual that we use PQ32 for the 3 magnetics. Probably the series inductor and the output inductor could be done with a different core or a smaller core, but the idea today was to show you why don't we integrate the magnetics? Why don't we create a single structure with the 3 of them? So we did it, and the idea is the following one, is to have the series inductor in the bottom of the transformer and the output inductor in the top of it. So it is very well known to do the series inductor with the transformer, but it's not so common to find the output inductor with the transformer. And the things we need to look at is, first, in the series inductor, it has the same switching frequency as the transformer. So each positive cycle of the transformer, both fluxes are cancelled in the common leg, and each negative cycle, both fluxes are cancelled. But in the case of the output inductor, we have double the switching frequency, which means that during each half cycle of the transformer, the inductor at some point will be added and at some point will be subtracted. But what is most important is that the DC bias flux will be always added, which means that we will have a DC bias in the common share leg between the output inductor and the transformer. What's the impact of this? The impact of this is some extra losses in the core, and that we will need to take care about saturation, because if it's not done properly, either the inductor or either the transformer could get saturated. So for this reason, it makes a lot of sense to have a customized shape where you have this core common share leg customized in a way so the system is optimized. So for this, we have a patent pending that we have now, and we have tested this configuration. We have built a prototype in our laboratory. Here. We have built a prototype in the laboratory, and we have tested, and you can find the results here. At the end, we end up with a solution that was very compact, 34 by 48 by 33 for the 500 watt. The total power loss was 5.81 watt. That this means it was only 0.13 watt compared to the previous case, and the overall temperature of the system is 96 degrees. So here we have a comparison between both cases. The one in the left, which is the classic one, we only grew up in the power losses 0.13 watt, but we could reduce the overall volume in 60%, and we have a very compact solution. But still, there are a couple of things to comment or risk or issues that should be taken into account. One is, again, saturation. If this is not done properly, the inductor or the transformer will get saturated. Here in the right, you have a picture of the AC ripple in the output inductor and the primary current in the transformer. As you can see, the output inductor is saturating, and this leads to the failure of the system. This happened because the flags were not properly cancelled. And then the second question that arises is that for this case of the integration, we have the inductor on the bottom of the transformer. So this means that we need a custom coil former to stand off the complete structure. So this means we have an extra cost, and we don't want that. So here we ask ourselves, why do we need this? What happens if we place the inductors together? What happens if instead of having inductor and transformer and inductor, we have the two inductors on top of the transformer? So nothing happens. The same happens. It's the same idea. We will have a flux cancellation between the series inductor and the transformer, and then we will have a DC bias flux addition within the two inductors. So again, we need to take some care about the saturation and about the extra core loss, but the system can operate perfectly. We did a prototype and we tested in the same conditions as before. We found some extra more temperature and some increase in the power losses. The reason was that the system was not prepared or was not optimized with this structure, but it can be done. It can be effectively done. So to conclude today, we have seen that magnetics are the key element in the phase shift full bridge converter. We have three of them. We have seen that having a leakage inductance as the series resonant inductance sometimes makes the difference. Sometimes it's not interesting at all, and each case has to be seen properly. And then we have seen that we have the three magnetics can be integrated in a very compact structure, achieving a high power density, and they can be done in either having one inductor at each side of the transformer or having the two inductors on the top of the transformer. Well, this proposed approach can be applied to any power range, as far as I mean, if you have everything clear on how the fluxes are going to be in the magnetics, it can be applied to any power range. Well, you have here some reference we have followed for doing this presentation, and now Jose Maria and myself, we will be happy to answer all your questions. Well, if you don't have time, please send us an email. We will be happy to do it by email.
Great. Thank you so much, Jose and Lucas, for your time. Please use the questions function to ask any of your questions. We will now start answering questions that came in during the webinar.
Okay. Let's go. There are a lot of questions. Let's go to the
Yeah. So if
Yeah.
we don't finish all of them, I'll be able to send you the Q&A report, and you can follow up on those questions if we don't finish all of them. So you could pick out a few key ones for the remaining time.
Okay, then we will start with one of the last questions, and well, I will make the question and Lucas can answer. I will read. Can we use it in closed loop for electric vehicles as DC-DC converter for 48-volt system?
Yes, I don't see.
Yes.
I don't see why not.
Yeah, this. I mean, actually, the motivation of this design is for DC-DC for automotive applications. Then, for sure, and the closed loop, there is no any problem of that. Only if where are you going to connect the measuring point that if you are doing peak current mode controlling at the input, there is no any problem. But if you are measuring the output or something, just be sure that we are connecting everything close to the magnetics, but no any problem. Well, this is interesting question from Teddy Bonin. What about isolation and capacitive coupling by having primary and secondary sides very close together? I think Lucas can answer this.
Well, isolation at the end is met by the layers, and I mean it's met by how you design it. If you leave enough creepage and clearest distance, creepage distance between the wires, and you have enough sheet of insulation, this is not a problem.
I think that if it's related with the transformer, because the question is primary and secondary, it is like a normal design where you have to take care. And the only point is that maybe you want to say something about the connections that the isolation between the connections.
Yeah, then when you have the other two magnetics on top of the transformer, there you need to be sure that you respect the clearance between the windings and the transformer for sure. But if you think about the transformer, it's the same as if you have it separated.
Related with the capacitance is the same. I mean, actually, in the case of the liquid inductance with the 3 microhenries, the parasitic capacitance was not very high, and was more or less in the range of picofarads, and it is not a problem. Well, there is a question of what is the temperature of the full power transformer.
The one shown in the slides is this power. These slides pictures are all at full power. Delivery 500 watt. You can see the voltage waveforms that we have. Full voltage in the input and full current in the output. This is for 500 watts, 400 volt to 48 volts. So it's 96 degrees.
Without
without any type of cooling. This is pure convection.
Any time,
yes,
pure convection. This is important. When 3 magnetics are integrated on a single structure, will not the MI affect the converter? Well, actually, when we are reducing when we are canceling some of the fluxes, this is improving the point. But what we have seen is that when you put all the magnetics together, you have like a kind of concentration of all the noise generated by the 3 of them. Then, when you are doing the mechanical design and you have to take care where to put the magnetics to be to take care of the MI, this simplifies the mechanical design. I mean, this is a very interesting point of solving the mechanical issues when you are working in a very high power density and you care about the MI. Then I think this is our first analysis is that this is a good solution for reducing the MI. Some question regarding that if we are going to provide a PPT. This is going to be safe. I don't know if they will also, but if you want to, you can write us an email to Frenetic and we will send you the slides. Okay, then there is no any problem.
The presentation slides and audio and video will be posted onto the Pels Resource Center shortly.
Just to clarify, there is one question: is there no leakage in the transformer, as you also have a series inductance? Well, we have in the leakage, but the idea is that for sure we are going to have. The idea is that we try to, in this case, to minimize the value that we have, and add another one because we need to have more energy to have zero voltage switching. Then, of course, that we have, but this is not enough. How do you measure independently core and winding losses?
This is a good question. Well, for this we have our own setup that we have developed here in Frenetic. So
this is what is part of the setups that we have here, and this is different kind of measurements and different kind of approach that sometimes we have to destroy a lot of magnetics, but allows us to make that measurement. What are the changes and effect according to the variation of leakage inductance?
Mainly one of the most important one, which is the effect of the proximity losses, because for instance in the two-chamber winding arrangement that we saw before, there you have a lot of power losses due to AC proximity. This is the main one.
Yeah, and also that when you have a lot of energy stored in the liquid inductance, you can have circulating currents, because think that the energy stored in the liquid and the resonant inductance at the end should be flowing somewhere. Then if you have too much energy, much more energy than you need, this energy will produce you a lot of problems. What is defined as high liquid inductance in percent, in absolute value? Well, this is a very good question, because well, depending.
It depends on application. It depends. If you have a 48 to 400, then you need to have very low liquids. It depends on application.
No, but I will say also that depends on the application, but also depends. The main value that limit the liquid inductance that you can have, or that you will have, is the tune ratio.
Yes.
No? I mean, if you have a tune ratio of 25:1, you will have for sure a liquid inductance relatively high. If you have a tune ratio of 1,
yeah, 1:1, normally you could be in the range of 0.5 nanohenries. So 0.5 microhenries. And if you go to 25:1, then you have much larger. So it depends a lot. The high, you cannot say a percentage value right now. It depends on application.
But let's say that for low values of tune ratio, you can have relatively low values of liquids, like maybe you can go to 1 or even lower value of 1. And for high values of tune ratio, is a little bit more difficult. Think that at the end there is the liquid is the parasitics, because you are not able to make a very good coupling. And the coupling between primary and secondary, when you have a bit different number of turns, even when you have parallels, it's very difficult to make the coupling with a lot of turns in one side and less in the other. Which is output power is possible for 1000 volt input and 500 volt output for efficiency? Well, I don't know. I mean, maybe we can make some numbers.
Yeah.
Will inductance leakage percent when connected to power filter parallel in full bridge phase shift? I mean, the leakage inductance appear in the, I mean, it's part of the transformer. Then will be in every transformer. The effects, if you connect to the filter, is well, depends of the connection, but which are you thinking about? But the liquid will not disappear. There is a lot of new questions. How was the switching frequency of 180 kilohertz arrived or chosen? That's a good question, but it was not the main.
It was not the main purpose. The main purpose was to design a transformer. So we know that the state of the art, or most of the people is working between 100 kilohertz and 300 kilohertz. So we thought one in the middle would be a good option, and 180 kilohertz seems to be a good option.
Yeah, it's not the purpose of the work was not to make an analysis of the optimal frequency, but we choose this frequency because it's one of the most common for this power level. We are working a lot with these power levels and voltage levels, and without using GaN or SiC, using classic MOSFET technology, 180 is relatively normal. How are the copper and core losses calculated, and the wire used?
Well, it depends.
Calculation, not the measurements.
Yes, the calculation.
We use Frenetic.
Yes, we use Frenetic, which at the end is based on our artificial intelligence. Yeah. Then, if you ask before, the artificial intelligence is trained based in real measurements and in analytical models, and these analytical models come from double equation, Bessel equation, modified estimates and estimates for the core. And then regarding the kind of wire is Leeds wire, which is very common in this type of transformers.
That actually the Leeds wire is selected for reduce the effects of the proximity losses and RAC. What is the difference in volume of magnetics in same power LLC and full bridge AC? I think that we have made some work in the past comparing these elements, but since the behavior is totally different and the approach is different, it is not straightforward. But I would say that the transformer sometimes can be used the same.
Yes.
The transformer can be used the same, but the rest of the magnetics are totally different, especially when you have the sinusoidal currents in the high sinusoidal currents in the resonance that are totally different. The FFT is totally different. No?
Yeah, it's completely, I mean, it's different approach for the transformer because it will suffer less in terms of the winding. Then the LLC inductance value normally is lower than in the phase shift full bridge. So in this case, in the LLC, you might be able to integrate it in a transformer. It makes a lot of sense there, but in the phase shift full bridge, you need much larger values. So it's not a straightforward comparison. Depends on its case.
What core material and design process will you suggest for 1 megahertz transformer frequency?
So here you can use 3F40, 45, I think is the name. Well, 3F36 goes up to 1 megahertz, above 1 megahertz. I think it's 3F40 something. I don't know right now the name, but yeah, you can look at the first few web pages. It's very good explainer. Yeah, 3F36 up to 1 megahertz, but above is 3F40.
Well, let's take 3F36 if you have 1 megahertz is working perfectly. Well, there is one question. Can you please comment on the fact that having a transformer with a high leakage inductance defeats the purpose of the transformer to be a low impedance galvanic isolation device? Well, I think that there is a mix of questions here, but the problem of having a high leakage inductance, well, a problem, sometimes it's used, but the problem is that you are having a lower coupling. I mean, that means that you are decreasing the efficiency of the connections in terms of the magnetics from the magnetic point of view, and also that the circuit will see a high inductance, with what happens is that you have limitations in terms of the slope of the current, and then this is something that will have effects in the like we see here in this slide about the duty cycle losses and also about this the effects in the tune ratio calculation. There are a lot of questions regarding the comparison between the full bridge phase shift over the LLC.
Yeah,
and
we can prepare an application.
Yeah, we can talk in detail later, but actually we have some previous presentations just to give some ideas of what, at least what I think is that the complexity of the design is different, and the complexity of the control is also different. But I would say that LLCs are much more common when you have like fixed point of flow solutions, and then you don't have wide input voltage range. Then you just made the design for having a very high efficiency and a specific point of working. But if you have a lot of wide input voltage or wide output voltage range, then you will have a very low efficiency points during the curve. Then with the full bridge phase shift, you can keep much more constant this efficiency, while the peak is not as high as in the LLC.
Yes, the transformer will suffer less, because if you think in an LLC, you might be operating between 65 kilohertz and 200 kilohertz for the same power. In this case, something like this. So the transformer will suffer a lot at 65 kilohertz in the core, then will suffer a lot at 200 kilohertz in the winding, and will have a really good performance in the middle. But if you look at the phase shift full bridge, you will have more constant efficiency.
Can this topology convert to bidirectional conversion? Well, but it's totally different. I mean, if you change the secondary diodes for another bridge, then you have a dual active bridge. But the transformer, I mean, the topology, I mean, the magnetic structure, at least could be similar.
Yeah, it's different.
I mean, similar. I mean that you can have the inductor and the transformer.
You can still do the integration, but
yeah.
using the topology, it's a different approach.
How to calculate the flux density in each leg to prevent saturation when using combined geometry? Well, this is a good question that we have explained.
You have to do the reluctance model. I mean, you have to do the model of the reluctance of each leg, and then calculate your flux based on the voltage and current waveforms that you have. You have to do some math there, but it's not too much. I mean, not too much difficult.
Just to go more in detail, at the end you have to make calculation of the density of your magnetic field.
Yeah.
Then for that you will need to know the areas of the area of the core that you are using. Then at that point you will see if you are saturating or not, and then try to calculate the new area for this case. If you made that reluctant model, that would be simplified first. That would simplify the calculations. Well, some question that looks like advertising. Does Frenetic provide any simulation tool to have an understanding of magnetic losses? Well, Frenetic provide designs. Then if you, for example, would like to have a design for some inputs for this kind of magnetic, you will have it. And the results are losses, magnetic field, but doesn't provide like equations, provide directly solutions, because Frenetic is based on models that are created with artificial intelligence, and there are we don't know what are inside the models. For us are just models that are started similar to the classic models of Steinmetz or Dowell, but they have evolved until today. how much the cost is reduced for these magnetic components. There are three main aspects that reduce the cost here. And the main one is that the material of magnetic material used is reduced at 16% more or less. That means that in the cores, you would have a 16% of production. You have to use a customized coil, right? But
it depends on, as we saw, it depends on the structure.
But the good point is that you can wind in, you can build winding manufacturing process that allows you to build in one, just in one time. Not with the same wire, of course, but well, with the same wire, the resonant and the transformer, but you can build in the same process. Then, if the manufacturing process can be connected, as we say, then for sure the cost of manufacturing will reduce it, and the total cost will be reduced. But the main part that has the materials, of course, that you have cost reduction. Where do we use classic and propose with respect to day-to-day life?
At the end, you need to look at your specification. You need to look if it makes sense in terms of efficiency, because the proposed structure is, sometimes it will give a really good benefit, but sometimes maybe to have to be below saturation in the output inductor, this means that you need to have a lot of currents, and might not be interesting if you have a huge DC output current. So it depends on its application. Yeah, it depends on its application. But it could be done to any application, but at some, for sure, it will not be so interesting.
What is the impact of series inductor over liquid inductance? Well, I think that what we have explained is that the idea of having as lower as possible the liquid inductance allows us to build a better transformer. And but of course that you will have losses in the series inductor, and
but there is no direct relationship. What I would say is that if you have lower liquid, you need larger series to match the one you want, and there is no other relationship more than that.
Yeah. Can we implement this topology for high voltage application? Sure. I mean, you have to take care with the
clearance and isolation, but yeah. Sure.
Yeah. Actually, our next plan is to use at 800 volts. Are there any high voltage ripples at primary side when secondary side switch, or vice versa? Where, what we see is that if we don't take care with the relation of the connections between the liquid and the transformer and the connections with the semiconductors, the parasitic inductance that appear there creates some spikes. But if you connect as close as possible all the loops that have interference in this operation, we didn't see any peaks. And regarding ripples, there is no, ripples could be because of some oscillations, and we have seen in the past oscillation between the liquid and the, well, maybe the output, the capacitance of the output diodes, but then you have to take care of which value of inductance or even the capacitor you are using, because the diode you are using. Does implementing zero voltage switching reduce the voltage spikes caused in the secondary side? Well, yes. The spikes, there are different phenomena for the spikes, but one of the main phenomena is that when you have a hard switching, what happens exactly during the commutation is that you provoke a spike. Then this voltage spike is reflected in secondary. And then, of course, that if you reduce, if you get zero voltage switching, the commutation will be much more smooth. Actually, here in in the presentation, you can see how clean are the commutations. Here you can see, and even in some cases, we see some spikes that are due to this relation, but not because of the zero voltage switching. Actually, here we have more. Well, here you can see that we have some spikes here, and this is due to one of these connections that is not as perfect as it should be. Yeah,
this is because of the power stage has some wires there.
What about certificate? Well, the point is that for the magnetic structures like this one, what you have two certificates is the creepage, the clearance, the isolation, the what else? I mean, all the mechanical solutions, but there is no any need for meta certification about the magnetic circuit structure.
So we're approaching the 11 o'clock hour. I just would like to thank Jose and Lucas for their time and their great presentation. I know there's quite a few more questions that I will definitely send over to you in the Q&A report, so you can either follow up or answer on your own. Please note, your certificate will be emailed to the address you provide within 10 business days. That 10 business days does not include Saturday and Sunday. And I would like to thank everyone for their participation today. This webinar has been recorded for future viewing and will be on Pell's Resource Center shortly. For information on upcoming webinars, please visit our website at IEEE-PELS.org. Thank you again for joining.
Okay, thank you very much. Bye.
Bye-bye.
You.
Bye.